to another episode of Planet Hunters Coffee Chat. I'm your host, Cassie Prolongo, and of course, joining me as always is a wonderful and delightful Nora Eisner. Hey, Nora, good to see you.
Hi, Cassie. Nice to see you too.
Excellent. All right. So, guys, I hope that you enjoyed some of our previous coding episodes because we're going to dive into coding today. I promised you that it was coming, and it is back now. So, Nora, what kind of coding are we going to be presenting to the citizen scientists?
So we're going to look at something that we have talked about a couple of times. I think we talked about it in the very first video that we did in the introduction. So we're going to look at code that you can use to look for periodic signals in a light curve. It's called a box least squared algorithm, or we call it a BLS algorithm. And it's the algorithm that the automated detection pipelines use to find periodic transit signals in test data. So we can run that code ourselves. So I will just very quickly go over kind of what the code does and how it works before we dive into the code. Okay, so hopefully you can see a slide.
Yes.
And hopefully it looks familiar.
Yes, I think we used this in our first or second episode, actually.
We did ion recycling. And it is, I think it's almost the same, but it's fine. We should go over it again. We did talk about it, but it was a long time ago. So I will very, very briefly go over how this BLS algorithm works. So we start off with just a light curve, and you can see there are transit events in there. We have 3 of those. Yep. So what the algorithm does is it takes the light curve and it chops it up into equally sized chunks. So if you imagine those black dashed lines are those equally sized chunks there. It then takes those equally sized chunks and folds them or phase folds them on top of one another. Now, because those equally sized chunks were exactly the same size as the duration of the orbital period, so the distance or the time between those black lines was exactly the same as the time between consecutive transit events. When we chop it up and fold them on top of each other, all of those transit events align. So we can flag this as a possible transit-like event because all the signals align. Now, I knew exactly where to draw those black dashed lines, how to chop it up, how to fold it on top of each other, but the algorithm doesn't know the orbital period before it runs this, because that's why we're running this algorithm, to find that orbital period. So instead, what the algorithm does is it takes the light curve, tries lots and lots of different orbital periods, and each time folds them on top of each other, those events. And you can see when that period is correct, then they align. And if it's not correct, those transit events don't align. No, so when they do align, when the algorithm finds a period where the transit events do align, it fits a box to that transit event, which you can see in red there. And that's why it's called a box least squared method, because it fits a box when that period is correct, if there is a correct period, I should say, and if it finds that and therefore flags it as a possible event.
Fantastic. Well, that makes entirely too much sense. Because when you first mentioned it, box lease, I was like, box what? Box lease? Okay, got it. So it finds that out. And for this particular one, the period was 3.80 days.
It was, yes. And you hopefully saw that period up there changed as it tested through those.
Yeah.
All right. Well, we can run this ourselves. So let's head over to a notebook instead. Which we can find.
And as always, everything that Nora is going over today will be uploaded onto planethunters.coffee, our website, so that you can go through it and run the test yourself.
Yes, it'll be uploaded as both a Jupyter notebook and as a Colab notebook. So you can run it either online or offline. All right. As always, we start by downloading the different modules that we need to run this code. You don't need to worry about those. You just need to run that cell. So that's this top cell here. Here this hopefully is looking very familiar by now. We're downloading data for a given target using the light curve tool. And we have chosen a random target here, tick 556528996. This is a tick ID that I do not know, but I just read out. We are downloading it for multiple sectors. So we're downloading it for sector 3, 4, and 5. So contrary to kind of the notebook that we had just last week, we have to use a slightly different command, just heads up, you have to use a slightly different command here if you're downloading data from multiple sectors as opposed to one sector. So if you're downloading data from just one sector, this word here is download, and if it's from multiple sectors, it's download all. So if your code crashes, that is the first thing to check, whether you have changed that to download or download all, depending on how many sectors you're downloading. But anyway, once you have downloaded...
Sorry, Nora, I'm so sorry to interrupt you. May I ask a very silly question? Why does it say that 30% of the cadences will be ignored due to the quality mask?
Oh, it's a good question. I think there's just a lot of bad data in this, so it was just ignored.
Okay. Sorry, I
didn't get question. So the reason why it's saying that is because light curve uses a quality flag. So it says anything that's flagged by the detrending algorithm or the extraction algorithm, so by the Spock algorithm is what it's called, as being potentially a bad data point, gets its own little flag. And in the light curve tool, it says somewhere in there that anything that has a certain flag should be ignored. So in this case, apparently there are a lot of data points that have been flagged. So about 30% of all the data points aren't shown because they're considered bad data points. That's not something to worry about. I just skipped over that.
Sorry, if I haven't seen that before, so my apologies. Sorry, I didn't mean to interrupt you, but yeah, okay. So we don't have to worry about that. It's totally fine.
No, that was a great question. Yeah, but yeah, we can just ignore that.
Okay, got it.
Okay, cool. So in the next box, we have the code that does this box least squared search. There's going to be a lot of code that I'm about to scroll through. You don't have to worry about this code. You don't have to write this code. It does have to be here, otherwise the code doesn't run. But we are just going to skip through it. Just keep scrolling. There are two functions. There's one for extracting the data and one for plotting.
For the light curve, okay.
All right. So we run the code that we just skipped through with one very simple function, and that's data underscore BLS. And then in brackets, we have LC. So LC is what we had, if we scroll all the way up to the top again, LC is what we downloaded and where we downloaded the data. So that LC, that thing in the brackets of the data underscore BLS, needs to be kind of what we called the downloaded data from light curve, and it needs to be a light curve kind of product.
Right.
So we can run that, and I have already pre-run it because it does take a couple of seconds or up to a minute, depending on how many sectors of data you look at. So I have already run it, and we have the results here. So we run the BLS, or the BLS is run, and that's kind of shown, the results from that are shown in that very top plot. And here you just have higher up on that plot means that it's more likely that that period is correct. So a spike in there, as we can see highlighted by that red line there, a spike in the black data there, it's a kind of high likelihood that that orbital period is correct. So at that point, all those transit events in the data would have aligned, and it was able to fit a box to it, and it was able to say, oh yes, this box fits, spike, higher likelihood, and it goes down, tests other periods, and these are less likely.
Okay. So, that's really, all right. So I'm looking at that first one. It's a little bit small to me, but I see where your point, that red. Oh, okay, great. All right. So it really spikes up there. Got it.
Yeah, so these are all the orbital periods that it tested. It started off with this orbital period. It said, oh, it's not that likely, so it's no. It then gets slightly more likely. There are certain periods in there that could be more likely, but there is really a big spike at 34.56. So that's highlighted as the most likely orbital period in this data.
So what is the second box there?
So in the second box, we have the light curve that we're looking at. This is just the whole light curve, and you have the kind of a model for those transit events drawn on in red. So this red kind of model here, this is with that orbital period that we just found in the first plot of 34.5 days drawn on. So this is to allow you to check whether the period that it found does make sense and whether it looks good. So that is also what we can do in that last panel there. Sorry, in that last panel there. Third one here is, here you have the phase folded data. So we have those two, in this case, there are just two transits. You have those two transits phase folded on top of one another, and you have that box least squared model, that box model on top of it. And this is a kind of a sanity check. It lets you check whether it is marking something, and it's marking something that makes sense, and whether that looks like it could be a transit event.
Interesting. So do you use the BLS algorithm? Do you go through and do this quite a lot?
So I sometimes like to do this check after, if we find, for example, a single transiting planet on Planet Hunters, I sometimes like to just run a BLS on the data as well, just to make sure that there is no other signal in there. So BLS is because it folds different parts of the light curve on top of one another. So it's building up signals of potential transit events. It can find things that are shallower than what we can probably detect by eye. So it can be a really useful tool just to check for additional signals. And speaking of checking for additional signals, this BLS, the algorithm hasn't finished. The BLS does run twice. So it runs it once to find the first signal. This is the most likely signal in there, or the deepest signal. But it then removes that signal. It just kind of blocks out that part of the light curve of where it just found a signal and runs the search again. So in the second search, it sees, are there any additional planets in this? And this is maybe something I would also do with Planet Hunters. I've removed the initial planet candidates, for example, a single transit event, and then run this to see what else it finds. But it automatically does it twice. First, it found a planet with a period of 34.5 days. And now it found a second planet with a period of 17.08 days. And again, it just kind of stepped through the different orbital periods, each time folding everything on top, or folding the light curve on top of each other at that orbital period, fitting a box to it and seeing whether that box fits. And if a box does fit, then you see a big increase in this likelihood of that period being correct. So we then see again, the same thing that we just saw before, this time in blue. You see those periods fit. You can see where they fall in the light curve. You can do a bit of a sanity check to see whether that makes sense. And here you can see those folded on top of one another with a box on top. That shows you that this is a good second planet in this system. Yeah. You can then also go to exopop, because this is one on exopop, to check whether it the periods that you found in this, if it is already a candidate on exopop, align with the periods listed on there.
Yes. Okay. So that was what I was going to ask. Do people have to bring over anything? We can do afterwards, going over to exopop to look at that ID, but bringing over anything from exopop, just remembering from the very beginning, you have the code, you have the data, you go in, so we didn't have to bring in anything over from exopop for them to run this code as well, right?
Nope, no additional information is needed from you, just the light curve downloaded with the light curve tool.
These numbers are just estimates and should be taken with a large pinch of salt.
They should be taken with a large pinch of salt. So these are estimates, especially, so the orbital period and T0, T0 is the time of the first transit, for both fits can be used. They can be good, but the transit depths, just remember, we are fitting a very, very simple model to this. We are fitting a box to a transit event that is not a box. So those transit events, those transit depths should be taken with a very large pinch of salt, but they can give you an idea of what the transit depth is. Just don't take them at face value. Right. Is my warning on that.
Cool. So we have, it looks like there's below another example. Is there one other thing that you wanted to run through with this particular test?
Yes, I just wanted to show one more example for reasons that will hopefully become obvious in just a moment. So this is kind of all the code you need for this. Once you've run the functions, the kind of the large chunks of codes at the top, you can just run it with just this many lines of code. You have the tick ID, we download the data. This time we're doing one sector, so we're just using this download open close brackets instead of download all. We run the code using df equals data underscore BLS with just the light curve in there, and then it runs. So the reason why I wanted to show this one is because the first time we run it, remember we always run it twice. The first time we run it, there is a clear signal. It is detected. There's a planet with a period of around 2.1 days. That planet is then removed and this algorithm is run again. And in this case, there isn't a second signal that is found, but the algorithm still just finds the most likely signal. So the algorithm will give you something as a solution. This is just what the algorithm says. This is the best solution. But this is why it's so important to check these plots, because there is, as you can see in the top plot, there is no solution that is significantly better than any other solutions, which is a red flag. When we see it fit, we can't see what it's fitting. at least to me, there's nothing obvious as to what it's fitting. And then this is probably the most telling one. When you see the phase folded plot, it is just a flat line. So we're not seeing anything here. So this, again, why we need to take all of these values with a large pinch of salt. These values are completely wrong. There is no second planet in this that we can detect at this level. So that's why you have to check the plots, and you shouldn't just quote these numbers just because they are shown to you. So this would be an example of where we can detect one planet using this method, but we can't detect anything else. Just keep that in mind when you run this.
This is a great example of having the importance of like a symbiotic relationship between running something and then having human eyes go through it, a second time. This is like a perfect example of that. And okay, and just to clarify, if you scroll up a little bit, okay, so even though there are spikes, there's not one that's significantly different and upscale, so that would be considered there's something ish going on, but not that there would be a second potential exoplanet candidate, because there's not one that's more obvious than the others.
Exactly. And so if you look at this scale up here, this is 1 × 10⁻⁵. The significance, or it's called the log likelihood, is very, very small. So these spikes are all very, very tiny. Whereas if we look at this one, this is much, much larger. This spike is much more significant. But even more than just those numbers, I think the most telling thing about this is that when we phase fold it, we can't see anything. There is just it's folding things on top of one another, but there is no signal there that we can detect. So this wouldn't be an additional signal.
There's no beep, there's no transit or anything. I'm thinking back to one of our episodes when Cole was talking about the heartbeat. Was it the heartbeat? There's nothing. It's dead. There's nothing there. There's just a flat line. All right, sorry. The caffeine's kicking in, guys. So I'm having a good time now. Excellent. Well, that was really good. I'm glad that you went through this. And as always, we're going to put it up on our website so that you can go through it yourself, both on Colab and on Jupyter Notebook. Nora is a wonderful explainer. That's why she's doing these fantastic episodes with me, because she's just very good at going through this. We hope that you have fun with it. If you have any questions, as always, ping us, drop us on YouTube, on social media. You guys, as always, make these episodes happen. So we hope that expands the breadth of your knowledge and toolbox with coding. We're going to continue on this. In coming episodes, though, we're going to dive a little bit more into reports and vetting reports, I think. Yes. And but if there's anything else that you want us to do a video about, let us know, because you are here to make these things happen. We're here for you. Okay, cool. Anything else that you want to mention, Nora, as we close out this episode?
No, I think that covered it all. Yeah, we'll dive more into validation reports next week, as you said.
Perfect. Excellent. Well, as always, lovely to see you, and good to see you guys at home. So take care and let us know what you think. Thank you very much, Nora, and I'll see you next week.
Thank you. See you next week.
Bye.